You haven't missed much, just 2 lemmas. So if what happens, if the function ls chi has a non-exceptional zero. Okay, so what's a non-exceptional zero? A non-exceptional zero, what is it? Trivial? No. Trivial zeros are not interesting here. I mean, they're never interesting, trivial zeros. So, no, non-exceptional means you remember what exceptional zeros were. I mean, we showed that there can be at most one exceptional zero in a certain place. It doesn't mean that there is only one possible zero, right? It just means that if you can somehow control the situation, then you have 1, 0, and this one is called the Siegel zero or the exceptional zero. So it doesn't mean that there are no other zeros. That is what I told you before, that if you can show that there is a Siegel zero, you will show that the generalized Riemann hypothesis is false. But if you show that there are no Siegel zeros, you do not prove that the generalized Riemann hypothesis is true. You just say that it is probably true. Okay, so there can be other zeros. So there can be some other zeros. It's not trivial. It's a non-trivial zero. Okay, so ls chi. If the function has a so my statement is not yet over. In this area, in Z minus S minus W, which is less than equal to R, then you remember the first lemma that we stated, there was a K between capital K and capital 2K. So that's going to come up now. There exists a K, which is a positive integer. K is between capital K and 2K, such that what happens, you have 1 by factorial K derivative of kth derivative. This is the kth derivative of f. That's my f, the f that I had defined, L prime s chi by L s chi, f of w plus r chi. This one is less than equal to 200. Again, I told you this, all the constants are somehow rounded up and made nice, and because actually how much do I care whether it's 200 or not? Okay, 200r minus k plus 1. Minus 1. So does this remind you of something? This kind of a result? You have a kth derivative, and have you seen such things in earlier in life? Not about L functions. Not talking about L functions. Some function. Just think of this as being some function. Have you seen such things? Yes. Where have you seen them? Huh? These are you use the Cauchy's theorem. Yeah. So Cauchy's inequality. Okay. So the proof will be to use. So proof. This is lemma 3. Okay. It's lemma 3, and we will use Cauchy's. Of course, you can already get that over here we are going to use Turan's result. Yeah, you can guess that. We didn't write it for nothing. So we use Cauchy's inequality for derivatives of when can we use Cauchy's inequality? Can we use them for any function? No. What kind of functions? You can't bring arbitrary functions and do them. They have to be holomorphic. Okay. For derivatives of holomorphic functions. Okay. So yes, what do I get? Okay. So then we get -1 to the power k okay, 1 by factorial k derivative, kth derivative of f s chi. This is equal to the sum of the zeros, 1 upon s minus rho to the power k plus 1 plus rho prime. This is the 1 upon s plus sigma 1 minus rho prime. Okay, plus some big O of 4 to the power k log t. Okay, so here I am now going to localize. So let S0 be equal to W plus R, and this is equal to 1 plus R plus IV. Let lambda be equal to AR for a constant, for a constant, but at least 1. Okay, it can even be equal to 1. Now you're going to do what? We have used 2 lemmas. If you haven't followed all the details of the proof, that you can do later, but you should at least know what the statements of the lemmas are. Which statement which lemma can I use now of the 2 that we have proved till now? Which lemma can I use? Does this look like something that one of the
that number of zeros in circle followed by log?
Yeah, so that's the density lemma. Okay, so use the density lemma. Don't worry, we are going to use all the lemmas. We didn't create the lemmas for nothing. So yeah. So yeah, I don't know where the word lemma comes from. You know the German word for it? Hilfsatz. So that's clear. Then it's something brought to help you. But lemma, I don't know. Probably it's Latin. So we use the density lemma. Now use the density lemma. What happens when you use the density lemma? So do you have some intuition about why we have this 4 power k? From where do you think the 4 power k turns up? There has to be some kind of dyadic decomposition. Okay, usually when you get this kind of powers of 2 landing up like that, from which you're going to break this up. Yeah. So so you take your rho minus w. You take this between 2 to the power j plus 1 and 2 to the power j omega. All right. And use the density lemma on this. For whom? For this one, you have 1 minus s0. Okay. So you take the sum now over the zeros, but at this point over the zeros, and you take this at 1 upon s0 minus rho, this one, s0 minus rho at k, this time it has to fall, right? You have k plus 1, so yeah, yeah. Now then what will happen? Take the derivative. So that's where I want to arrive. So minus 1 power k, 1 pi factorial k, derivative this one k, f s 0 chi. Okay. S0 chi. Okay. This will be equal to, write out the definition, 1 upon S0 minus rho k plus 1, take the derivative of this, plus the second term, derivative of 1 upon S0. The second term, it's no longer on the board, but remember this one was delta 1 minus rho prime, okay? And this is k plus 1. So the first one is over rho and the second one is, and then you have the big O of lambda to the power minus k log t. Okay. So in which case will this be true? This will be true if lambda is less than equal to 1/4, because that was a condition in the lemma. And this one, so I have sigma there, sigma minus so rho minus w. This should be less than or equal to lambda. So, and this one, rho prime minus delta 1 minus omega should be less than or equal to lambda also. All right. Now you've done this. So what do you want to do now? So you see we have broken this into two parts. We have taken between 2 to the power j omega and to the power j plus 1 omega. So you should do it repeatedly. Okay, you use the density lemma again. All right, density lemma, use it again, and if you do that again, repeat the use of this till who is complex? Omega, what was, oh yeah, what was omega? Omega was 1 plus IV, I think, wasn't it? Yeah. So what's the problem with it?
That for the 10 minutes.
You take the principal part, probably. I don't know. I think so. I think you choose a, huh? Yeah. Yes, I think so. I think so. Should believe that. Do that again. You use the density lemma again. If you do that, what happens? You get the number of terms for n terms. Then you get n is bounded by lambda log t. N is the number of terms. Because every time you get a bound, then for the number of terms, you get lambda log t. Now you can use the first lemma that we talked about, which is Turan's lemma. Now use Turan's lemma. So for using Turan's lemma, you will have to choose some capital K, and it says that if K is greater than or equal to N,
No, that omega could be replaced by lambda. It will basically not circle of radius. So that should be lambda. Depending on lambda, you are dividing that difference, then summing over.
for the first time the density lemma should, when the first time the density lemma, yeah. Because this doesn't make sense. Now I agree with you. Is this okay?
That left and right. That
Yes. Wait. Let me just. Let me. Yes, of course. I mean, that's why you created the lambda here. This is why you created the lambda here. So that's fine. This is fine. That was your problem. I understood. I understand now what your problem was. I was thinking lambda, but I was writing omega. So that was the problem. So my my head and hand were not coordinated. So now I want to use the Turan's lemma. Who's going to help me with Turan's lemma? So what was Turan's lemma? What was it?
We consider a set of complex numbers that capital K,
Yeah?
then we can find a small k from capital K to K.
Yes?
The sum that Z1 to the power K to Z to the power, this was bounded by something. It's not Z1.
Something, yeah. Okay, so let's do that. So if I take a K, if I take some capital K, which is greater than or equal to this n, okay? We take this, then there exists some little k, which is between capital K and capital 2K. It's so such that what happens if I take 1 upon factorial K, this was my beginning of K, f of S0, then this should be greater than or equal to, so that was 50 for the way it was stated was 50, and you can take it here as 0 minus rho 0, okay, to the K plus 1 minus, there'll be some more terms, O to the lambda minus K, because I have a K here, okay, this is going to give me a lambda minus K log T. All right. So what is rho 0? It is a non-exceptional 0. That's what, do you remember? We said that what happens if there is one. So, yeah. So rho 0 is a non-exceptional 0 in LS chi. So rho 0 is a non-exceptional 0 in L S chi with S minus is less than equal to lambda. So if there exists a rho 0, then with rho 0 minus omega less than equal to r, then what happens? Then S0 minus rho 0 should be less than equal to 2r. Okay. So now I want to do something with this 1 by 50 S0 minus rho 0 K plus 1. So this one, I want to bound this, yeah, the right-hand side of this equation. So I want to bound this. So 1 by 50, it's this 1 by 50, S0 minus rho 0, K plus 1, okay, minus this term, an error term, O K to the power, lambda to the power minus K log of T. This is going to be greater than or equal to, what you get here is, this is 2r, therefore 1 by 100, 50 becomes 100, 1 by 100, K plus 1 by 100r, K plus 1, and this remains the same. Lambda to the power minus k log t. Choose some a, let it be more than 200. So if you choose your a, take it to be more than 200, then you get 200 here from that. So 200 divided by a to the power k. This is, remember, little k was less than or equal to 2 times big K. So this one can be written as 200 by a to the 2k, and that's less than or equal to 200 by a. What was our constant? C4. C4 R log T. All right. So I need 2 times this. So I choose A to be equal to 400 to conclude. All right. Hmm? Hmm? Where is the problem I haven't figured out? Yeah? Yeah.
And it should be only k instead of 2k. Then
Ah, yeah. Yes, because it's greater than, little k is greater than k. I'm sorry. Yeah. I'm sorry. Now, yeah. So I have to finish this proof one day, right? I will state lemma 4 and not prove it. All right? Oh, you look so happy. I'm not going to give you a proof of lemma 4, but it's similar to lemma 3. Yeah. In Bombieri's book, these are called lemmas A and B. This is probably the first time we are doing a theorem of some contemporary person, right? Did we do anything else? I mean, we know Grozov and all that, we haven't seen them. Grozov proved it in 1937, and Landau is a picture somewhere. Yeah, is it? No, I think this is the first time. So the statement is long. The proof is also long. I will not do this proof. Okay. So this is now another lemma. So lemma 4. And then I promise you that's the end. If we have lemma 4, then we straight away now go to Bombieri's theorem. Okay, so here is lemma 4, which uses lemma 3, okay, and nothing else really. It uses lemma 3 and Cauchy's inequality, or all of that you know. So I take some r, which is between 10 to the power minus 4 and 1 by log t, and you take your omega and v as before. Okay. And then you claim that there exist positive constants A, B, C, and C5 positive, all of them positive. In fact, the big A should be a little bit better, such that if LS chi has a non-exceptional 0, you remember that is, we talked a few minutes on that, non-exceptional 0 in S minus W less than equal to R, for all x which is large, greater than t to the power b, because then this integral, this time you have a result with an integral between x and x power a, and you have a sum between y and x of AP. I will tell you just now what AP is. P to the power W. W is the W of the lemma 4. Chi of P. This thing is square dy by y. This is less than or equal to C5, some positive constant C5, and effective. These are effective constants, okay? They can C5 log x cube x to the power minus A, B, what are my constants? A, B, and C, so CR. Okay. So what is AB? AP? AP is, I'm claiming that it has a non-exceptional 0, but I'm not claiming anything about exceptional 0, therefore I have to do the case distinction. So AP is equal to log P, if there are no exceptional zeros, this AP is log P if there are no exceptional zeros, or no exceptional character, which is the same thing. If no exceptional character exists, and if it does, then you add a factor for it, log P to the power 1 plus, this is your exceptional character, chi 1p. This is your exceptional p to the delta 1, if not. All right. So no proof given. today. Okay. Does not mean that there is no proof. But the only thing that's used is lemma 4. Use, no, lemma 3. Use lemma 3 and Cauchy's inequality. Okay. So if you are stuck, then you read Bombieri. (1987 or 8), I don't remember. Okay, it's an asterisk notes. So this is, it will be called lemma B in this. Okay.
Statement is less than equal should be greater than equal.
For
C5 down.
no, it's less than equal to. Is it? Well, since I haven't written the proof, wait, let's see what lemma 3 does, okay? Lemma 3, in lemma 3, yeah, so if you use, yeah, okay. But that will create a problem, right? Ah, no, it won't. It won't. Sorry. Yeah. So, yeah, with some luck, we will now finish the proof of. Now we have done. Now you can assume that you know all these lemmas, okay? Assuming that you know lemmas 1 to 4, we can prove, and the two theorems which we stated before, that is Landau-Page and the zero-free region. And assuming this, we can now prove theorem, Mommier's theorem, which I stated in the. I did, right? I stated the theorem. So now proof of Bombieri's theorem. This is theorem 14 in his book. Okay. So now we use Landau-Page, and we assume that we can assume. So we are counting the zeros, right? So we can assume that our alpha is less than equal to 1 minus some constant that was C1 by log T. Okay, because what would happen if it were not, if by then, okay, if not, if it were not the case, then n would be 0, all right? N alpha T chi would be 0, yeah. So n, if you take an alpha bigger than that, alpha T chi is 0, so it's not interesting. We look for some, we can forget this altogether and then move to the next page. So now we will take rho to be equal to beta plus I gamma, and this will be a non-exceptional 0 of Ls chi. Okay, be a non-exceptional zero, and we will show that there will be some contradiction. Non-exceptional zero of LS chi for what? For beta, which is bigger than alpha. All right? So we are going to take some radius now. We will take our little r to be, which C are we at? We had C6 last, did we have C6? C5? Then C6. C6, 1 minus alpha. Okay, and this constant is at least 2. C6 is at least 2. And this was the C1 that we had, the C1 from Landau page. So this, it's greater than 1 by C1. Okay. So our R is now between 10 to the power minus 4 and 1 by log t. When does this happen? This can happen if alpha is greater than 1 minus 1 upon C, because 1 minus 1 upon, so this constant C, and then the other bound that we had, which was 10 to the power 4. Yeah, it was 10 to the power minus 4. So we will assume this, okay? That, let us assume this. Let this be true. If this is true, then if I have rho minus 1 plus IV, this is going to be less than or equal to 1 minus beta plus gamma minus V. And this is less than or equal to R by 2, because R is, and then I need to bound gamma minus V. This is also R by 2. So the whole thing is less than equal to R if gamma minus V is less than or equal to R by 2. All right. Now use the last lemma, which said, by which you could bound your, yes, it was greater than, I remember, now I can. So use lemma 4. What happens when I use lemma 4? So I take the integral between gamma minus R by 2 and gamma plus R by 2. All right. I take the sum between x and y of AP that was done in the, there is our AP, it's still there on the board, p to the power 1 plus IV, okay, lambda p, this whole thing square, dv dy by y, and you go on an integral between x and xa. Okay, so this is going to be using lemma 4. Okay, this is bounded by r log x cube x to the power minus CR. Okay. Now you take the sum over the zeros. Okay. So that was our aim in the beginning. Do you remember? So we take the sum over the zeros. And you get, so our modulus is bounded, and then we have the n, this was the number of zeros, alpha t chi. This was our number of zeros, and the sum was for all q which is less than equal to t. And this, once you have done a little simplification, this is going to be less than x to the power CR log x cube x to XA. I'm just copying y to x. I'm just copying from over there. Y to O. Something went wrong. No, it's something went wrong because it's y to x. Okay. Copy it again. AP square p square, and a bit of calculation shows that this is p plus t to the power 5 dy by y. Okay. So could we stop here? I'm very tired. I've been talking for a long time and drinking this chalk. And then I want to show you a bit of the end. And then I want to tell you why I made you suffer so much. It was because something good will happen at the end, and that this repulsion. First, there are two reasons I made you suffer. I made you suffer because then you would have seen a proof completely. And then I will use it for the equivalence, not an equivalence, for an implication. It's not an equivalence, for an implication on the non-existence of Siegel zeros. And that is a very recent result. It's 2 years old. Okay, by all living mathematicians. I mean, a result that's 2 years old is usually by living mathematicians. One among whom is a very young person. So that's to tell you that I mean, mathematics is going on. It's not over. It's not over with Riemann and Landau. Okay, so let me just stop now and go on after lunch. Okay.